all of you. So thanks for this. Yeah, as you can see from my background, I have a nice picture of the space, so the Martian yard that is in Stevenage, for example. So that's a picture that I took personally on that. So I visited the Airbus Defence and Space over there. And of course, I will also talk to this mission soon. I could see the field where the navigation algorithms, guidance navigation algorithms of the European rover have been tested. So the ExoMars mission. Okay, so for this reason, essentially, I will enjoy essentially also myself on this. Let's present. Can you share the screen first of all?
Oh, yes. Also, sorry to disturb. Before starting, can we record the session? Is it okay if we record the session?
Yes, sure.
All right, thank you.
I think that it's already recording. I saw the message, or not?
Yeah, I was just confirming.
Okay, yes. So that's the. Let's talk about my background. Okay, I'm not only doing rovers. Actually, I just joined this kind of field of space research a few years ago. Not before. But before that, I did a lot of things related to guidance, navigation, and control of space system in general. So my expertise, if I can say like this, is more related on altitude and orbit control of small satellites, space data system, space robotics intended as a space manipulators, or let's say catching object in space, or manipulating, let's say, space debris or things like that. Control of spacecraft flying informations, autonomous rendezvous. So more or less for a lot of years since I was a student, I somehow developed this kind of skills related to the guidance, navigation, and control of the space systems. Recently, somehow I started to apply those kind of knowledge also to some more terrestrial, let's say, applications. So, for example, launchers. So developing, at least studying with some students, guidance, navigation, control of launchers, as well as essentially developing GNC algorithms for smaller rovers. And that's essentially something that also I'm proposing some IRP during these years. Yeah, more or less, this is my background. I just wanted to introduce myself in this way. I can talk to you for hours about this kind of topics, but today we will focus probably on autonomous planetary rovers. So let's start. And actually, it is a coincidence, but today is the 12th of April. And 60 years ago, the man somehow accessed space for the first time. So I have here a nice picture of Yuri Gagarin, and today is essentially the 60th anniversary of that particular moment. That was a milestone for future missions, of course, for the conquering, I guess, the exploration of the space, and it opened essentially new frontiers for the humanity. And there is this kind of let's say this kind of event somehow triggered a lot of other events. For example, let's say the exploration of the space by US, Russia, and so on, that somehow have is continuing even right now with the future missions that are aiming, for example, to reach, for example, Mars in 10 years or even 20 years or something like that. So there is this kind of trend of putting humans as a, let's say, operators or somehow people that are operating within the space. But in general, having human in space is not, let's say, is somehow limiting and somehow imposes a lot of constraints on the space exploration. And indeed, let's say there are some particular conditions, some particular challenges that somehow are limiting the space exploration by astronauts. First of all, astronauts need to deal with space environment. So they when they are essentially orbiting around the Earth, they are exposed to space radiation that somehow can damage their cells. Microgravity that can essentially reduce the muscular mass on humans, and of course those will provoke some long-term effects on human bodies. And of course, if we want to, or we are expecting to aim for having a mission towards Mars, where humans need to somehow fly for months on a space capsule, those kind of effects needs to somehow be mitigated. Furthermore, the mission, the human presence is also expensive in terms of equipment and mass that we need to bring to support, let's say, life of astronauts in space. And so there are costs associated to launch and so on. So it's very somehow challenging build a mission that somehow can aim for example, to reach other planets with astronauts, as well as it's extremely difficult and risky. So we need to have a plan for extravehicular activities and deal with the health and safety of astronauts and so on. And that's essentially the reason why having robots simplifies a lot our life as engineers. So we can explore somehow planets. We can essentially operate space just having essentially operating remotely those kind of devices, those kind of robots. The key aspects of space robotics can be summarized essentially in those kind of key words: manipulation, teleoperation, autonomy, mobility, versatility, resistance and survivability to extreme environment. And we will see them during this presentation. First of all, let's say we need to make a distinction between two different applications, and today we will focus to the second one. So the first application is having space robotics in space, intended as let's say space outside planets. And in this case, for example, we can have missions like the ISS, where there are different robotic arms that can operate or can move along the ISS. We can have humanoids kind of robots that are essentially helping astronauts or certain kind of tasks. We can essentially also retrieve, let's say, material from space, or, for example, catch orbital debris, as in the second image that we see over there, with some robotic manipulators. But today, essentially, we are more interested on space, planetary and space exploration. And of course, I think that all of you knows that those kind of missions, so inside mission, like Curiosity, and right now Perseverance mission, and so on, developed by NASA, for example, that are aiming to explore and analyze different properties of those planets, even with the final aim of understanding whether or not life is possible for a future exploration by humans over there, or even colonization, and we will see this at the end of the presentation. So this is essentially the topic of today. We can start defining some keywords, let's say, that are very important for understanding why we want, let's say, robots in space or in on a planet, and why essentially we are operating with these kind of devices. First of all, rovers, as well as, let's say, any robotic platform going on a planet, allow for manipulating objects, so taking, for example, samples from the ground, putting instruments on specific positions of the surface to analyze, for example, the atmosphere, but as well as the soil compositions and so on. So there are different functions that are only possible when rovers or robots are accessing the site. And yeah, this is essentially done either on a planet as well as in space, essentially. Mobility. We want to reach, we want to explore the surface of a planet. Mars is probably the closest planet to the Earth, and of course this is essentially the most common target for rovers. And Mars essentially is not flat, but it's like the Earth. So there are mountains, there are rocks, there are sands, and so on. So we need to somehow build rovers that are capable to move on this kind of environment. And that's what was the most important challenge for NASA when was developing, for example, rovers like Opportunity, Spirit and Opportunity. So try to find a way, a sort of autonomous platform that could somehow move freely on this kind of environment and avoid one of the most of the obstacles that the surface, Mars surface has. And of course, this kind of challenge resulted on developing a technology that right now is currently still used by the rovers that are exploring Mars right now, so Perseverance, Curiosity. So sensing and perception, let's say, are important, as well as, let's say, the mechanisms of the suspension mechanism that are characterizing this kind of rovers are quite particular and developed for this kind of rovers. We can imagine to use essentially robots as in two different ways, let's say. The first kind of let's say commanding option is to just teleoperate the rovers and the robots. And this is quite easy if we are close to the Earth. So, for example, if we have a robot that is on the ISS, we can probably imagine that we can teleportate it also from ground. But this is not possible in some cases, actually in the case of Mars exploration mission. Why? Because of the lag, or let's say lag between the Earth and Mars. So in some cases, we can reach even up to 30 minutes of lag, telecommunication lag between the two planets. And this is, of course, one of the major challenges for rovers in general. Why? Because, of course, we cannot imagine to teleoperate the rovers with this kind of delays on the communication. That's why we need to have an autonomous system that can take decision when specific condition will appear, or in any case, when let's say we need to explore essentially a certain area without any feedback provided by operators on ground. And that's one of the major challenges that the rovers are facing in general. And more or less is going towards a more, we need to make somehow a distinction between even having an autonomous system or automatic system. And I think that you are an autonomous society, so you will probably have, you know, this kind of difference. But whenever you are having a system that responds to specific and well-structured conditions, so in a deterministic way, so if there a certain kind of condition is happening, then the system reacts by taking some action. We talk about automatic system, while when we are living in a non-deterministic environment, so for example, like the Martian surface, where we don't know exactly what to expect in the system, and the rover has to, in any case, travel by himself and take decision more or less autonomously. Of course, in this case, we are talking about the autonomy of rovers, and that's why essentially right now most of the rovers are more or less semi-autonomous. Let's say there is still a little bit of human interaction, but most of the, let's say, short-term decisions are autonomously taken by rovers, by Curiosity, by Perseverance, and so on. For example, I put always this kind of image because it's quite nice. Just to give you an example, let's suppose that we are our rover is located over here, like in the Confidence Hills. The operator with the camera more or less can, so we can get images at a certain point, assuming that the rover is momentarily stopped, can take images of the surrounding area and pick specific points where the rovers can go. Now, the path that the rover will follow is not known, but we can, the way that usually NASA is planning the mission is scan the area, surrounding area, with let's say a stereoscopic camera, and then the operator at certain point during night, let's say, picks a point and says to the rover, you need to go over there. And of course, you just wait those kind of 30 minutes for communicating this. Maybe you wait 30 minutes just to be sure that the same message essentially is sent twice so that we don't make mistakes on the communication. And then the rovers autonomously selects, so scans the area with the cameras of the stereoscopic camera, maybe uses some algorithms to detect the different objects that are rocks that are over there, and autonomously somehow plan for, let's say, the best path that somehow allows him to reach that particular point. And that's essentially what is happening right now with why when cut this writing the slides. Sorry, but I see someone that is writing. Okay, so that's essentially what is happening right now. Rovers themselves are supposed to survive extreme environments, and that is another good characteristic for that differentiate from, for example, humans. So they are more or less not affected by any microgravity effect. They can more or less resist to extremely high and low temperature, high vacuum, corrosive atmosphere, ionizing radiation, very fine dust. So there are some specific characteristics that enable rovers to explore essentially these kind of regions, even when we have, for example, a dust storm, as in 2018. You can see essentially two images over here, taken from two different moments, where essentially you can see that the second image is way more way less defined than the first one. Why? Because we have a dust storm, so essentially you couldn't see too much in depth what is happening over there. And this was essentially so. In any case, curiosity could survive this kind of harsh environment. Let's talk about a little bit of story. So I just want to give you some key missions that have been developed during the years, just to understand even how the technology somehow developed during this period. The first rover was a lunar rover and developed by Russia, so in 1970, Lunokhod 1 and 2. And it was very, it was a sort of toy. Let's say that right now probably everyone is able to build. So it's even a very, very technology. So essentially, you had 8 wheels, okay, that were supported by a dedicated suspension mechanism. He could travel, let's say, order of 37 kilometers, let's say, and it was controlled from ground, and so teleoperated from ground, with essentially television image based technology. So it was a really TV signals in the old-fashioned way, so analogic signal and so on. And the same, and the commands also were somehow provided with analogic technology. And that is essentially what was in the 1970. US more or less developed as the first rover from US was essentially the rover that explored the lunar surface together with the astronauts in the Apollo missions that go from 15 to 17. Even in this case, the rover was operated directly by the astronaut, because at that time, of course, we didn't have the capability of having autonomous system or even automatic system. So that came later, sometimes let's say, or that could automatic system that could deal with, let's say, unstructured terrain as this one. And of course, this was another rover, but oh, sorry, I just don't know. Over here, essentially, we have also other landers. For example, the Viking was famous in 1772. The Mars Phoenix landers, Mars 2 and 3 landers from but finally, let's talk about the proper Mars rovers that somehow is a family of rovers that was developed by NASA since 1997. The first Sojourner mission, so the Mars Pathfinder mission, was essentially a small rover of only 10 kilos, more or less the same size of what we are aiming right now to have in our lab in Granfield. So very, very small rover that somehow at that time could just travel for 100 meters in 3 months. We had solar panels, you can see over them those kind of solar panels. And it was tiny, small, and somehow the autonomy was a little bit constrained. He didn't have essentially a stereoscopic camera, he had only one camera, and there was somehow quite so the operation could take quite a lot of time, even because at that time we couldn't have so much processing capabilities to embed on that platform. Things get better in 2004 with a quite famous Spirited Opportunity mission. Those kind of rovers, like those ones, were essentially quite famous. But I just remember when I was young that those missions and how essentially those missions evolved and what they could explore. So, and more or less the technology developed in such way that we could extend, for example, the autonomy of those rovers for up to 30 kilometers. So they could travel, for example, the overall lifetime of Opportunity, 9 years, he could travel for 30 kilometers on the Mars surface. Spirit, same, could essentially travel quite a lot, up to 7 kilometers in 7 years. Then they got broken and they needed to leave it where it was. But one of the good things of this kind of missions was that the navigation systems used by those rovers were somehow developed and somehow optimized for those missions. And right now, essentially, we are still using the same kind of technology that at the time was developed. So stereo vision camera and panoramic cameras are still embedded in Curiosity, as well as the suspension, rocker bougie suspension system is right now a standardized suspension system for planetary exploration and also terrestrial exploration, and was again developed for those missions. So this kind of, for example, suspension system allows the rover to climb rocks that are bigger than the wheels that are of the rover themselves. And yes, Curiosity. Let's say the evolution of Spirit of Opportunity led us to have the most famous mission up to a few years ago, and right now we have Curiosity, but Perseverance. So the second edition, let's say, of the same typology of rover that is 900 kilograms mass, and it is powered by a radioisotope thermoelectric generator, while the other two platforms were essentially were using solar panels, essentially, generating the. Let's focus on curiosity, because more or less the same instruments are embedded in Perseverance. So really, they don't change a lot. Actually, they are just, let's say, a sort of small evolution of, what was embedded in Curiosity. In particular, let's focus on the navigation instruments, because, yeah, we are talking about autonomy. So the key aspect of the autonomy is, of course, trying to understand what are the sensors that allows us to get information. So having a perception of the environment. And those instruments are the mast cam, which is essentially this kind of general tower that is located on the top of this kind of tower, let's say, of the mast. The nav cam and HADS cam. The nav cam are essentially actually four cameras that are located over here, let's say, and are essentially stereoscopic camera that allows us for having a stereoscopic view of the area, of the scenario that is surrounding the rover. And just to give you a dimension, this tower, so from the soil to the tip of this tower, we have a altitude. So this tower is like 2 meters high. Okay, so it's quite high, and so you can have essentially and scan, let's say, the area from almost 2 meters over the surface. And while the HADS cam, so the camera that are somehow detecting hazards for the rovers, are somehow located on the bottom side of the rover, so close to the wheels, so that somehow we can, the rover is able to detect whether or not there are objects that are crashing against the wheels, or having some rocks, for example, that are somehow dangerous for the wheels of the rover, or not. So in this way, essentially, you can detect hazards for the rover itself. Yeah, as you can see here, I put two nice images from one article, and you can take essentially the reference over here. So the first one is the stereoscopic image taken from the NavCam, and you can see essentially how you can pair the two things from the two cameras in order to obtain a three-dimensional image. And then, of course, I put also the more or less what is the field of view of the rear HADS cam, so the camera that are essentially located on the back side of the rover, so the ones that are over here, and with some specifications. If you're looking at the specifications, you can notice that those cameras are, the optical characteristics of those cameras are quite similar to the one that we are using on Earth applications. Really are sort of small webcams and things like that, with the field of view of 45 by 45 degrees, focal length that is 40 millimeters. So yeah, it's more or less a small webcam, at least for the NavCam. For the HADS cam, actually, we are using fisheye cameras. So they are essentially, for example, we have a field of view of 180. So we are able to scan the overall ground on the surface. Another key characteristics of, let's say, perseverance, but as well as of curiosity, is the way that this kind of system lands on the surface of Mars. I believe that you have seen already those kind of videos, but I want to propose them. So what I will do is just exit the presentation. I just need to find a way to put. Can you see the?
Yes, we see your screen. We are seeing YouTube.
YouTube, yes, exactly. So just to give you an overview of what happened a few days ago, essentially, actually a few months ago, this one in February. So after the interplanetary travel, essentially the capsule detached from the main body of the spacecraft, and somehow started to land. We have a thermal shield that somehow reduces the heat input to the rover. A parachute is deployed to somehow reduce the velocity of the capsule, and if you believe that this will land in this way, but no, this is not enough. But we want to land in a specific position of Mars. So what is happening is that we deploy essentially our rover with a sort of thruster mechanism that somehow will navigate and try to find the best place where to locate the rover itself. You can see over here essentially how it's reaching the surface. At a certain point, the rover will be deployed with some cables, and then essentially the thrust and let's say that the thruster will be essentially crashed in another location. So at this point, essentially the rover will start all the operations for deploying his sensors, and that's it. Start exploring Mars. This is, let's say, just an animation. The good thing of Perseverance is that they have shown also the live videos coming from Perseverance. So right now in YouTube, you can see the descent and touchdown of Perseverance with the real cameras that have been recording this event. So it's something very nice. So for now, there is a parachute that have been deployed. More or less, we are navigating, and those cameras are not only for recording, but are also trying to understand where we are aiming to. You can see how essentially is the system is oscillating. For now, we are still with the parachute. Right now we started essentially with the engines, so with the trusted phase. Right now, essentially, we are on the trusted phase, and more or less, we are trying to find the best location for placing the rover. And now it's deployed. You can see the rover that is just going down, attached to the. So, and we succeed. So they succeed essentially, and of course that is was a very challenging operation. You can see how complicated was this operation for. And why? Because the mass of the rover is 900 kilos. And of course, we couldn't land it only with a parachute, that amount of mass. So the velocity that the final velocity probably would be too high for, or the parachute would not able to provide enough drag to land in a safe way 1,000 kilos of mass. And that the only way that NASA and scientists had for having essentially a safe approach or a safe touchdown was essentially to have this kind of trusted phase that was somehow designed and successful, I would say. Well, right now, essentially, the rover itself is not alone. We have also another small copter. So for now, we are going and moving towards a new frontier of space exploration, not only having rovers, but also copters that somehow can fly on Mars. And that's something that it's happening just right now. I believe that more or less the first flight is planned for today. So you can even go to the NASA website after the meeting and see whether or not Ingenuity succeed on flying on Mars. I think that they have some issues, so I'm not sure if today they are performing the first test, but maybe we can get some news soon. And Ingenuity is essentially a copter, really a small demonstration mission that somehow has been developed in order to demonstrate that it's possible to fly even on Mars, and that is a challenging thing. Why? Because the atmosphere of Mars is very rarefied. So the blades that are characterizing, let's say, this copter are totally different from the blades of a normal copter that is flying on Earth. And they are optimized for really interacting with the rarefied gases. Yeah, that's it. Essentially, that's the thing. What I can do is somehow show to you more or less again the kind of operations that will be performed or have been performed in those days. So we have our rover that somehow will release the copter, and I think that right now you can even take so you can find on YouTube or other images the real images of this kind of operation. So the rover itself will start essentially operating, flying quite soon. And the idea is that this kind of rover could go further than so this kind of copter could somehow go further far away from the rover and explore area in order to, for example, map a wider region and then allow also the rover to plan for a better, say, path to reach specific points. So that's the demonstration mission. So you can see that now we will take off. And well, it will go away. You can believe, and I can somehow I got essentially some papers on that. You can believe that the technology that is embedded on the copter is so advanced that you will never buy those kind of devices. That's not true. The board that is embedded over there is a commercial off-the-shelf board that you can buy for a normal drone application, and it costs okay, £1,000. So it's not so big expense, so expensive. Why they did like this? Just because they wanted to have demonstrate that this was possible also with code technology. Yeah, more or less, this is what I wanted to show to you. Let's go ahead with the presentation, even because I'm quite going late. So what I need to do is stop this meeting and yeah, talk about let's say the wheels. So in general, this kind of rovers have 6 wheels with a rocky bungee suspension system, as I already said. The 4 of the wheels, so the ones that are on the extreme, so essentially the 2 in front and the 2 on the back side can steer for 360 degrees. So this will allows essentially the rover to even translate on the other direction. And essentially, again, the rocket bungee suspension system allows for climb over, let's say, rocks that are larger than the rover's wheel. And one of the problems that essentially Curiosity had was that after a lot of the wheels themselves started to deteriorate. You can see essentially over here that they started to break. And that was one of the issues that right now has limited the capability of Curiosity, that is still operating, but of course it cannot travel so well because of these kind of damages. And that's why also Perseverance, somehow they have studied and improved the kind of wheels. Right now, essentially, they came out with a totally different configuration in order to avoid this kind of the generation of the wheels. And this is a study that is done also from ESA side. And over here you have a clear image that how essentially the wheels are designed. So ESA, for example, has this kind of wheels, and I saw them when I was in Airbus in Sweden for a visit. So you can see that even though they are metallic wheels, somehow they are designed in such a way that can guarantee a certain degrees of flexibility in order to somehow adapt over the surfaces and so on. Again, I can put a video just to show you this kind of thing. Yeah. And this is a mission device. So it's ExoMars, so it will be launched soon. It might be also be launched right now, but it will land in Mars soon. Can you hear the sound?
No, unfortunately, no.
Can you see? Can you hear the sound or not?
We only have video playback. There is no sound.
Sorry?
We only have video playback. There's no sound.
Ah, fuck. Okay, that's bad. Okay, so I will try to explain what is happening step by step. So I'm just go ahead. So more or less what they are trying to do over here is try to test the way that essentially the rover will be get out from the base that somehow landed on
For
the
interrupting.
surface. So more or less they there is this kind of platform, and let's say the wheels will adapt to the surface conditions that of Mars. So you can see that, yeah, I wanted to show you, let's say, how the wheels are designed in order to simulate what essentially is usually done on ground with, let's say, polymeric wheels of tires and so on. Yeah.
Oh, Dr. Felicetti, just real quick, I'm pretty sure you're just missing a box that you had to tick when you started sharing your screen. So if you want to, you might be able to just stop sharing, and then when you start sharing again, there's a box that says share computer sound or audio, something like that. And you just have to
Okay, I will try then. Advanced sharing option. How many participants can share at a time? So multiple participants can share simultaneously.
It's not on advanced options. So just click on the button that says share screen. Then you'll see.
Share sound. Yes. Okay. That's the. Yeah. Right now, probably you can see.
Yep.
With
Yeah, it works now.
Yes.
Works. Okay.
before we went for 5 degrees. Now we are moving up to 15 degrees. If before I was nervous, now it's even worse.
So they are trying to simulate the different, let's say, inclination condition that the platform can have when it lands on the surface. And of course, the operation gets more dangerous. That slowly get out from the platform and essentially climbing. Okay.
The rover has to.
So I will go ahead, but more or less that was what I wanted to show to you, as well as let's say what is happening when we have a sending environment. So send on the surface. So
long before landing on Mars, Curiosity had to prove herself
in order to somehow test whether or not the rover can travel on this kind of
on Earth. But in the Mojave Desert, it's hard to get the full Martian experience.
We have to deal with all these different things that are unique to Mars. Gravity's the biggest one. Mars gravity's 3/8 of Earth's gravity. So we had to build a whole nother rover that weighs on Earth what Curiosity weighs on Mars.
It's really fun to, like, every once in a while kind of leave the office environment behind and come out to an environment like this and see what the real rovers are going to be doing on Mars.
So one of the things that I wanted to show to you is this one. So this kind of prototype is similar to Curiosity, but of course weighs way less. Just because essentially the gravity in Mars is 1/3 of the gravity of Earth. So somehow they try to reduce the mass that is pushing the wheels on the surface, and this way essentially you are reducing the friction that you can have from the soil. And of course, in this kind of environment, you also have. Another nice thing of this kind of picture over here is that you see those kind of balls. Those are essentially reference frames for the motion tracking system. So they were essentially also having probably, you can see over here some tripods with some cameras. And this is an equipment that we have in the lab. So essentially what we will try to simulate probably with some students this year is this kind of
on Mars.
Kind of conditions. So even in our
that's what we should do is dig in all 6 wheels, have it sink down so they're completely embedded as though it were in an avalanche, and see if it comes out.
We're potentially burying the side wheel, the middle wheels.
Let's get it really stuck.
Okay.
Yeah, that's what I'm trying to do.
You know, my dad said I was always going to become a ditch digger, and maybe he was right. We could shovel more in there, but I mean, it's up to its axles, right?
We're really starting to sled now. Look at it go. Yeah, once the wheels drove over the mounds.
By the way, what I'm learning here is
more or less, let's say they are playing with this kind of rovers, and one of the good things of this is exactly that it's a sort of game, and you enjoy playing with it, and try to test different conditions. But let's move on, even because it's taking a lot of time. Wheels are a problem. Then, of course, we have all the navigation system, so the terrain mapping and planning of the trajectory is on the softer side, probably the key challenge of autonomous navigation. And this is essentially done, in different ways. There are different studies and so on. Curiosity and Perseverance are using a stereo camera-based navigation system. So still not, they are not using LiDARs. That's for a specific reason. But the tendency on the research is try to understand whether or not we can embed LiDARs also in space applications. One of the key challenges of using LiDARs on space applications, there are essentially 2 drawbacks on using LiDARs on space applications. The first one is that LiDARs produces a lot of data that needs to be processed in almost real time. And the technology of the onboard computer that are flying on this kind of mission is at least 20 years old. So you can imagine to process those data with a computer that was made in, let's say, 2000, let's say, a sort of Pentium or whatever. So that is probably not still not feasible for space, at least for this kind of big application, big missions. Why this is done? Because of course all the components needs to be space qualified. They need to somehow be tested against radiation and so on. So the technologies are somehow is lagging. Space technology is somehow lagging on this. So some terrestrial applications that right now are somehow common, autonomous, let's say, navigation of cars and so on, in space is not possible. The other key point is the structure of the soil. So having LiDARs on rover can help up to a certain point. Why? Because the soil is, yes, structured, but we don't have, let's say, trees, we don't have any obstacle that can be detected easily with a LiDAR. They are just rocks. And of course, the rocks can be merely seen from, let's say, multi-beam LiDARs, but not you cannot have a full 3D reconstruction of the environment when the environment is almost flat, let's say in this way, or not very defined. Okay, so with the hills that are not well defined. In any case, yes, what we can do is try to apply localization path planning on those kind of maps generated with 3D cameras or with LiDARs. And for example, we can use even images for doing feature detection and tracking, for example, for visual odometry. So one of the common algorithms to estimate how much the rover has traveled is based on the visual odometry. That is very, very helpful, especially when we have a slippery terrain as the Martian one, sandy terrain as the Martian one. Why? Because essentially the wheels will tend to slip on the sand, and of course the tracking of the visual features of these kind of smalls will give us a better understanding of much travel the rover did. Another characteristic is that compared to normal autonomous system, we don't have any aided navigation. So we don't have a GPS, for example. So we cannot use a GPS because we don't have any constellation around Mars that is provided by GPS here. And path planning, again, we can use more or less the most common path planning algorithms that are terrestrial application, even to plan, let's say, the trajectory of the rovers, gravity, gradient-based ones, or other kind of path planning mechanism. Yeah, I will skip essentially this let's say presentation, but more or less it's the same presentation that we have seen before, but just on Steven Angel, let's say. And I will talk just 2 minutes on the research that we are doing at Cranfield on the rover, planetary rover site. And we started, as I mentioned, me, Luca, Zanotti, Fragonara, and Jay, to supervise some of the master students, like you, essentially, on, let's say, on a specific topic that was essentially, yeah, LiDAR-based SLAM and path planning for planetary rover. By using, let's say, initially the aim was to plan for an experimental setup. So we have those kind of the rovers on our lab. We have a motion tracking system on our lab, and we wanted that essentially to build, let's say, our knowledge on this kind of autonomous navigation based on those kind of platforms. The platform itself is a very, well, it's a sort of toy for now. It's called the Leo rover, like my knee, essentially. And we wanted to use a LiDAR that was our lab. Well, then COVID happened last year. We couldn't do, let's say, experiments, but we are hoping that we can do this year. What we did is simulating it. So the two devices are those ones. So the Leo rover, Leo rover platform, plus let's say some quite good, I would say, LiDAR. It's an Auster one with 64 pins, so channels that are scanning contemporarily. So we can do a 3D. Let's say the construction of the environment in theory with that, yeah, you can see the range is 100 meters, so it was quite a nice device. And yeah, we were trying to implement this with ROS. So we did some simulations. Initially was just basic, simple one with a very simple structure in gazebo. Let's say, yeah, you can see some studies over here, we tried to simulate, for example, in gazebo, a typical Martian scenario. So we took somehow images from the missions, from the Mars database of the images, and we detected essentially small stones, and let's say we try to map essentially the same configuration of stones and planimetry of Martian terrain in gazebo. And more or less what came out was a configuration like this. So you can see even right now that a LiDAR cannot probably work well over here because, of course, the altitude of the rocks and this, let's say, the difference in altitude of the surface is not so good. And yeah, anyway, we tried, and we started to plan for let's say autonomous navigation algorithm for exploring the area. And yeah, you can see that we can apply, for example, a SLAM algorithm to detect the edges and see what's going on over there. And yeah, you will with time, essentially, the rover will essentially explore even a wider region. And over here, you have essentially the region that have been explored at the end. I can go a little bit ahead. Now it's moving. It's detecting other rocks, let's say, over here. And yeah, we are aiming right now to reproduce the same kind of results with a real hardware. So that will be one of the students that this year will focus on this, on our smaller playground that we will need to develop. Yeah, more or less, this is it. I just want to conclude this with, let's say, a futuristic view of what will happen in the future. For example, there was this kind of study that was developed by one of my colleagues for a proposal for a space colonization in Mars and so on.
Our first step on the surface of the moon.
Yeah.
Today, there is renewed passion to explore for our next human endeavor. Mars, the red planet, further than any human has ever been. We face many challenges: remoteness, no livable atmosphere, high radiation, dust storms, and extremely low temperatures. Before any humans set foot on Mars, we must first design a protective shelter. We will protect our astronauts from radiation with a thick 3D printed shell structure using Martian regolith, which works great in compression but does not perform well under tension. To overcome this shortfall, we have chosen to construct the pressure-retaining parts of the habitat from lightweight inflatable pods. They will be made out of high-precision engineered composites that are prefabricated on Earth. Their elliptoid geometry will be able to mitigate the pressure differences whilst optimizing spatial planning. To create the base on Mars, we will use a two-phase approach. In Phase 1, an ecosystem of 3D printing robots will arrive months in advance of any human explorer. They will construct the protective shield for the base by adopting a modular robotic swarm strategy, a plan that allows for redundancies and enhances the odds for success. Intelligent autonomous robots will have interchangeable roles, from battery storage to scout rovers, logistics to excavational, and even 3D printing units, all integrated with multiple cameras and sensors for navigation. They can reconfigure themselves for a multitude of purposes, ensuring prolonged usage beyond the initial build phases. The smallest configuration is the one-wheeled scout rover that uses ultrasonic scanning to analyze the Martian surface to determine the best regions for obtaining optimum regolith. The digger receives the location coordinates and then excavates the Martian soil. It then delivers the payload to the refining assemblies. Here, large chunks of Martian regolith can be processed down to a finer grain and then delivered to the melter robots in situ. They then use concentrated microwaves to melt the regolith and extrude through the 3D printing nozzle. The shell is autonomously 3D printed, layer by layer, over several months by the robotic system. In the next phase, the first astronauts arrive with the habitation units, equipment, and supplies. The robots now take on their second life roles to aid the next phase. They come together to make flexible mobile platforms that can carry the payload from the loading zone to the base. The convoy begins its journey across the Martian surface to the habitat site. The build commences with a connector module placed underneath the protective shield and ready for inflation. The module then unfolds and self-inflates into its final form. The habitation units are then placed into position and sequentially inflated to form the completed pressurized environments. The circular layout of the habitat ensures continuous accessibility of the habitat in the event of a catastrophic failure. Each connector module houses 3 integrated environmental control life support systems, delivering essential services like power, water, data, and oxygen to all the habitation units. A circular conduit delivers these services to multiple endpoints in each pod. The base will be remotely powered by 2 nuclear kilopower reactors and a solar farm, located a safe distance away from the base. In the next stage,
Okay, I just stop over here because the nice part of the rovers was the construction part, let's say. But yeah, at the end, the result will be essentially a nice environment like this one, let's say.
Shop with digital fabrication facilities,
With
the sleeping quarters with gym facilities, and immersive virtual reality platform. We believe that the key to success of human habitation on Mars is the health and well-being of its residents. Creating a place where work, life, and living combine holistically to ensure they feel connected to each other, to themselves, and somehow to their distant home.
So this kind of study was essentially a study that one of colleagues of mine, so Dave Cullen, did in collaboration with sort of architectural studio or something like that, sort of proposal that was somehow competing in a challenge by NASA, let's say, so organized by NASA. And okay, they developed essentially this kind of concept, even from, let's say, design side, but as well as from the feasibility side with this kind of rovers that were more or less operating and so on. So, yeah, more or less, this is something that might be in 20, 30 years, we will see. You never know, that technology is quite ahead, and probably, let's say, we will reach Mars, at least we will explore with once in Mars, but of course we need to cover some technological gaps that right now are still limiting us. For doing that, for sure, we will somehow use rovers, we will use robots to build, let's say, this kind of infrastructures, maybe first on the moon and then maybe on Mars, but in any case, the idea is that this is going ahead. Just to finish, I put here some references that I am, for whoever is interested, book chapters of space technology books in general, but there are also 2 good, or at least 1 good book on planetary rovers by Ellery, this one, that is essentially sort of Bible of everything related to space rovers, let's say. So planetary rovers, robotic exploration of the solar system, 2016. You can find it even probably in the library. This book. For any further question, we can talk right now for a moment. Let's say whenever you want. Let's say I don't have any constraints. And yeah, if you want, you can contact me. I'm always happy to answer questions, have a discussion with you, having meetings, and maybe see whether or not we can have also some joint projects in the future. You are still in Cranfield after summer or something like that. Thanks for your attention. It took a little bit too much time, but I hope that you can accept this. Let's say.
Yeah, that's okay. Whoever couldn't stay for this long probably already left, so that's okay.
Yep.
Yep. So first of all, Dr. Felicetti, on behalf of everyone here today, thank you for taking this time to give us an insightful and entertaining presentation on planetary exploration and autonomous rovers. I'm sure everyone appreciates having this area clarified. And also, I want to thank you for effectively helping multiple courses come together today, because as you can imagine, this is one of the very few topics where automotive and space engineering courses come together and intertwine.
Yeah, it's true. I totally agree, and it's one of the good thing of having rovers is that you need let's say both the expertise, let's say from a space let's say related point of view, but as well as from autonomy and automotive point of view. So that's
Yeah, it's a little bit of both. Okay, so now let's open a Q&A session. So anyone that has a question, please unmute yourselves and speak up. If you don't want to speak up, you can always just drop them in the chat.
Yeah, thank you very much for the presenter. You've given us an insight into the space technology. Honestly, if I had gotten your lecture much earlier, maybe I should have considered taking a career in space technology. It's quite interesting to me. But looking at the challenges that we have at the moment, and coupled with the new form of applications in artificial intelligence, how can the space technology use this for its own intended applications and for the huge success for missions in the space?
We are moving on that direction. So having AI, artificial intelligence embedded on space system is what is under investigation right now on both space applications as well as planetary applications. Having AI on rovers, it's obviously important. You need to detect hazards. You need to detect let's say, specific structures that somehow can point out that there is something interesting to explore in some directions. And of course, this comes with the improvement of the technology that have been used for developing those kind of courses. So, for example, Perseverance has been developed 10 years later than, say, Curiosity. So, the onboard computer that Perseverance has is a way more efficient than what Curiosity had. So at that point, essentially, a lot of applications that are involving also AI are feasible now rather than, let's say, 10 years ago. So for sure, we are moving on that direction, and that is one thing that is important. Yes. And I hope that I answer on your question. Let's say.
Yeah.
We had different meetings in the community explicitly on, let's say, AI application for space. And this comes essentially on, let's say, downstream applications, so applications that then will have and provide services to the community on the Earth, but also on AI for, let's say, space exploration. And that is also something very, very challenging and interesting. And yeah, I can say that there are conferences on these topics, people that are talking about these topics, and yeah, we are moving on that. Even on detecting faults. So another good application for AI is fault detection, autonomous fault detection of systems. So we cannot rely on human operators all the time. So the space system needs to detect what is faulty by itself and maybe take some action to repair itself when it's operating. And that is something that somehow is also a good application of AI for because we cannot access and repair. So the humans cannot go on Mars and repair the rover. So this needs to be done. Let's say autonomously also. Okay, for example, that's another good application.
Yeah, thank you very much. That was even the area I was trying to push up to, because of we have started making applications for this in the IVHM Center, where we're using artificial intelligence in looking at the faults in most of the systems that we're working on. So I was just having that in mind, that if that could be applicable to the aerospace, it should also be applicable to the space technology. Thank you. Okay.
Sure. Other questions?
If nothing, if nobody, I have a couple of questions.
Let's go ahead. Let's
Okay,
see.
the
Then we
first
see.
The first one is, I'm curious which SLAM algorithm you're using for the simulation with the Leo rover.
Okay, we tried the cartographer, but it was quite
Cartographer.
Yeah, but it was very, very demanding in terms of computational power required. So we needed to find a simplified version and things like that. So yeah, that was the study.
So you are using information from the inertial measurement unit and the LiDAR.
And LiDARs, yes. That was the
Okay.
Yeah, the topic was a little bit yeah, it was for now just simulation. The best thing of this was just it was but yeah, we are trying to do this with real hardware right now with some NVIDIA Jetson and things like that. So maybe have good results this year across the thing.
And then when it will be the time to possibly simulate with the real robot, where can it be on campus?
Well, we have a sort of experiment, a sort of lab. The first, so it's actually, I think that you know that it's IMEC, the ground floor. There is an area with a motion tracking system. And that is the area where we were supposing to do the experiments last year. So we'll be for now indoor and probably in a structured environment with some boxes and so on. So we will try to start easily with the easy tasks. But yeah, in the future, you never know. Maybe we can go outdoor and just put the rover somewhere and see what's going on with the, let's say, non-structured environment.
Okay.
Yeah. That's it. Yeah. For example, a good area was just in front of the new, let's say, building. The aviation center, how it is called? This Dartec, just in front. There was a road that was used for the autonomous navigation car that probably your department is developing. But on a side, there was also another playground that was essentially for let's say for out track, let's say navigation, and maybe that can be a good place where to test these kind of things. But yeah, we need to see what's going on. Yeah.
Thank you.
Other questions? Questions, comments, curiosities. I really, I'm quite happy to answer.
How is it possible to guarantee the fidelity in the training of the neural networks, for example?
It's a good question.
When training the robot in the desert and like moving it then to Mars, because
That's
the landscape is completely new.
That's a good question. It's something that you can somehow train up to a certain level, but then of course you need to, for example, rely also on even let's say virtual reality. In case train on with simulation software, this kind of things. For example, there are, let's say, researchers that are developing sort of suite for simulating space environments or planetary environments with for image detection algorithms or things like that. So that's something that is also part of the research in general. Okay. So yeah, you need to use this kind of tricks or create a database that can be somehow more or less good for this kind of applications. Other things? Other curiosities, other things? So one of the things that maybe I can show is this photo again. That was taken from myself on. You can see the platform. That is this one. Let's say over here. Okay, this one. Right. That was just for made for testing. Let's say the camera. So the motion. Let's say a sort of a small prototype of a rover for testing the camera system and let's say the basic movements of the rovers. You can also look at the top, let's say the roof over there, let's say, you see over here. So you can see some images, some kind of pictures over there. And that was used by the engineers of Airbus for having a sort of ground truth of the position of the rover. So with a camera that was pointing on the sail, and by looking at those kind of let's say images, you could essentially locate in a quite accurate way the rover on the field. On the ground field. So it was a sort of autonomous navigation system, let's say, based on a camera is looking at some structure and the images. Okay. So and that was a trick that the Airbus engineers that develop in order to have let's say a motion tracking system made. In this playground. Okay.
Thank you.
Other things?
We have a question in the chat.
Yes.
It's from Tiga, if I'm not mistaken. He says, I'm curious on how the Mars rover can assess the terrain traversability as a reference for its path planning.
Yeah, That's a good question. I can assess when it goes there, probably. So if it gets stuck, no, probably there are, even in this case, some image processing techniques that can be used for understand whether or not terrain is full of sand or it's rocky and things like that. So of course you need to find the best path. So that's probably the way. So it's always assessed by using images. And yeah, the wheels in any case also you can detect essentially that something goes wrong whenever you are pairing the wheel odometry with the wrist odometry. So if you are comparing the two things, you see essentially that the wheels are moving, but you are not going ahead. Probably it means that you are getting stuck soil and things like that. So you need to probably change let's say strategy and go in another direction. That is, for example, something that is has been studied, for example, in this kind of field, in this kind of things. Okay. Other things?
All right, so last chance, guys, because it's getting late right now.
Yeah.
If there's no more questions, I think we should wrap this up.
We have a lot of people who thanked Dr. Felicetti for the presentation, and I also want to thank him because it's been really interesting.
Yeah, I'm trying to do my best for make things enjoyable, but yeah.
It was.
Sometimes I succeed, sometimes not, but I hope that this time I succeed. Let's say.